So yeah, so this talk is on a sort of sub-project of the main project that we've called Trustchain, and it's an attempt at a decentralized approach to public key infrastructure for applications in digital identity. And if we go to the next slide, please, Sam, just to introduce us, I'm Tim Hobson, part of the research engineering group in the Turing, as are the other people you can see here. Sam is going to be doing half of this talk, but there are also three more REG members, Lydia, Luke, and Pamela, who have contributed to a large extent to this work. Okay, let's go forward to the program. So I'm going to hand over to Sam in a moment, who's going to do a demonstration of a particular use case involving verifiable credentials, just to set the scene, give an example. Then I'll come back and I'll talk a bit about the theory behind this idea, public key infrastructure itself, and how we're planning to upend it. And then Sam will then sort of demonstrate the command line software that we've developed so far, and talk a bit about how it achieves some level of security and robustness. And then finally, we'll move on and just mention our next steps and plans for future development. So I shall let Sam take it away with the demonstration.
Okay, thanks, Tim. So we'll start by just introducing a use case straight away, which is for verifiable credentials, which is that of digital degree certificates. So that we'll use this this scenario throughout the talk today to illustrate Trustchain. So if we imagine someone, say Jane Bloggs, who's just been to a university and received a degree from that university, and now she'd like to receive a credential to prove the degree she's received. So one way of doing this is to use verifiable credentials. So the setup here for this involves a credential on the right-hand side. And this contains information about the subject and their degree that they've received. And what the university can do to make this into a verifiable credential is they can sign this with their key. So upon signing, a proof is added, which is a digital signature of the message that was in that credential. They can then pass this verifiable credential to Jane, and then that's for her to hold. So we'll just demonstrate that first process in the command line using the Trustchain app that we've developed. So the Trustchain app is called Trustchain CLI. So we can just look at what's available. So you can have DID or VC functionality. We're going to use VC functionality for today. And then the options under VC are attest or verify. So we'd like to attest because we're playing the role of the issuer here, the university. And what we do is we'd like to attest to some credential file, and we'll be using the DID of us as the issuer, which is the University of Oxbridge in this case. So let's just have a look at the credential file that we saw on the in the slides. So that's the same there, and we'll pass this file now into the app, and we will use the DID of the issuer, which we know already, and we will save this output to a new file called vc.json ld. Okay, so that's done, and now we can take a look at the VC, and as can be seen, it's the same credential as before. The issuer has now been added, which was us as the University of Oxbridge, and the most important part, of course, is the proof, which includes this JWS JSON web signature, and you can see it was just created just now. Okay, so we've got our VC. What next? So Jane's got the VC and she'd now like to use it. So she is about to start a job, and the employer would like proof of her degree. So Jane provides this VC to the employer, and the task for the employer is now to check that it's indeed a valid credential. So before we move on to public key infrastructure, I'll just demonstrate that we can do that as well within Trustchain. So we now use, if you remember, we've got either a test or verify. So we'll use a verify this time. And the flags that can be taken are, you pass in a file, you can verify just the signature only, which is what we're going to do to begin with. And you can even specify root event time, which we'll come on to later, because this is Trustchain specific stuff. So just verifying the signature only, the readout just gives us a tick, assuming that we had the public key of the issuer already. Okay, so going back to the talk, the key question now is, how do you get the public key of the issuer? And secondly, how do you trust the key of the issuer? So I'll pass back to Tim to talk about that.
Brilliant. Thanks, Sam. Yeah. So I guess the idea of public key infrastructure is familiar to most, if not all, of this audience. So I'll breeze through this quite quickly. But yeah, if we just skip on, please, Sam. So yeah, so this scenario that we've just seen, of course, it depends. The whole idea, the whole system depends crucially on the verifier knowing the correct public key of the issuer. And if somehow they end up with the wrong public key, then they could be tricked into accepting an invalid credential. And of course, if we just skip forward one or two, it's certainly impractical and insecure for there to be sort of bilateral exchange of public keys between the verifier and the issuer, even if they know how to contact each other. And so, the problem of how to securely and reliably share public key information is absolutely fundamental to this system, and that's the problem that Trustchain aims to solve. If we go forward, please, Sam. So a good question to ask at this point is, well, why don't we just simply rely on the existing public key infrastructure that's used on the web to secure communications? And of course, that's based on trusted third parties called certificate authorities who issue certificates to domain owners. So in this model, the verifier would get the public key from an X509 certificate of the issuer, or more likely they would actually submit the credential to some web API which is secured by that certificate, and then they would just receive a response. I think although this is quite an appealing idea, there are actually good reasons why the web PKI is not really suitable for applications in digital identity of this sort. And a good way, I guess, to understand that is if we put ourselves in the position of the verifier. Suppose we've submitted a credential for verification, and then we receive a positive response. Well, how do we know that we can have confidence in that? Really, the verifier is, in that scenario, is being required to have trust in the certificate authority, first of all, to have appropriately vetted the issuer, and in some way to have established that the issuer is the appropriate authority to issue credentials of that sort. But really, there's no mechanism to guarantee either of those things. We don't really know. The certificate authority itself is an opaque entity. We don't really know who or what they what they're doing, and they don't have the real problem here is that the relationship between the certificate authority and the entities that they certify is somewhat artificial, in the sense that it doesn't correspond to some genuine relationship that actually exists in a physical world. These certificates are basically issued on request after some procedure, some vetting has been done. But this relationship is kind of manufactured on request, purely for the purpose of sharing public keys. So if we go forward, please, Sam, to maybe keep going a little bit more. So now I'd like to consider a more decentralized approach to public key infrastructure. Thanks, Sam. So what we're sort of aiming for with this work is a public key infrastructure in which the trust relationships are really just digital representations of actual genuine relationships that already existed in the physical world, and those are between legal entities that are recognizable to the users and the participants in the system, which is obviously in contrast to the certificate authority model. So here are some examples of some of the sorts of hierarchical trust relationships that we would like to be able to express. And the arrows here are representing a kind of attestation from one authority about a subordinate entity. And each of these chains of trust, if you like, leads back to a root, and we'll explain how that root of trust is established in a moment. But in our university degree certificate example, I think it's fair to say that the appropriate authority, at least in the United Kingdom, to attest to the identity of a university would be the government department for education that oversees those universities, and an appropriate authority to attest to the Department for Education, or DFE, would be a central government entity, which in this case acts as the root of trust. And there are lots of other examples. One here is, perhaps we could have a central bank as a root entity, which would then attest to the identity of the commercial banks to which it grants a banking license. And then those banks in turn can attest to the businesses that they lend to and provide financial services to. So in this model, all the trust relationships are all transparent. They're recognizable to the users of the system. And so each participant can then properly judge for themselves the level of trust that they're prepared to place in each chain. But to achieve this, we need a more decentralized architecture, or rather infrastructure. So if we can go on again, please, Sam. So fortunately, there's already an industry standard for sharing public keys in a much more decentralized way, which is the W3C standard for decentralized identifiers, or DIDs, which is where this diagram comes from the standard document. And it shows the same workflow that we've introduced in Sam's example. So a DID is really an identifier for a legal entity. It could be a person or an organization, and that identifier can be used to resolve certain information about the entity, including their public keys. And the W3C standard specifies that this information should be obtainable from what they call a verifiable data registry. And so the system we're about to demonstrate builds on this standard, and it specifies exactly how this verifiable data registry is to be realized, and exactly what's verifiable about it, as opposed to merely sort of trusted. And in fact, there are two distinct problems related to this data registry that we need to solve. The first is, how do we publish DID information in a way that makes it easily accessible and is complete and can be verified in some sense. And the second problem is, in a hierarchical system of trust, how do we agree on a particular set of keys that's going to form the root of these chains of trust? Right, so if we go on now, I can actually explain how the trust chain system works itself. So first, a quick note that it relies entirely on open source software, open protocols and networks, which makes it inexpensive, but also robust, resilient, secure. And that no new or dedicated infrastructure is needed. So in particular, we rely heavily on a system called ION, the Identity Overlay Network, which is a network based on open source software from the Decentralized Identity Foundation. And what ION does is it enables us to publish and resolve these DIDs and DID documents, the data associated with them, in a way that's verifiable. And it does this by embedding information in the Bitcoin blockchain, which is then effectively immutable, and which refers to an address on the IPFS distributed file system. And those files on IPFS contain the DID document information, which includes the public keys themselves. You can see in this diagram. So the first step is to publish a root DID using ION, so that it becomes anchored in the Bitcoin blockchain. And what's unique about Bitcoin, or more specifically, the proof of work consensus mechanism that Bitcoin uses, is that it gives each transaction a timestamp that can be independently verified by anybody at all. So the timestamp on that transaction can be verified without needing to trust anybody. And that's going to be important because it means that provided everyone agrees on the date at which the root transaction was published, then everyone can identify the correct transaction itself, and it can't be faked, if you like. And of course, that transaction commits to the public keys of the root entities, which we're assuming are recognized by all the participants and users of the system. So it could be the central government being represented there. And now if we go on to step 2, please, Sam, thanks. So then we wait for some time to pass, and that ensures that the root transaction really can't be mutated or removed from the blockchain. It's just infeasible, and it's not feasible to do that after the longer time has passed. And we can then publish what we're calling downstream DIDs, which are DIDs that contain a signature from one of the root entities, which is an attestation as to the validity of the data that's contained. So in our example, if the central government entity is represented by the root DID, then in the first level of downstream DIDs, you'd find one representing the Department for Education, and those downstream DIDs are also embedded in the blockchain, with a reference to the corresponding DID document on IPFS. Step 3, later still, those downstream entities can publish their own downstream DIDs to create chains of trustworthy DIDs and public key information. And some of the links in this chain could be simple attestations, while other ones can actually delegate authority to extend the chain further. And finally, in step 4, we can see the verification process. So now anyone who wants to access and verify the public keys associated with a particular entity just needs to resolve the chain of downstream DIDs and verify the signatures on each of them, and then finally to verify the timestamp on the root DID. And we assume that everyone agrees on that, because it's a relatively easy and small amount of information to share the actual date on which that was published. And because all of this depends on open and permissionless protocols and networks, really any community can just pick up this system and just use it to create a digital representation of the trust relationships that are relevant to them and their community. And then that infrastructure can be used to issue and verify credentials in a trustworthy manner. So hopefully, having explained the concept, I'll pass back to Sam to demonstrate some of these operations in practice.
Thanks, Tim. So yeah, to make this more tangible, we'll return to our use case before, where Jane is presenting a verifiable credential to an employer, and the employer would like to verify this credential. So this first step is that they need to retrieve the key of the issuer on that credential from a verifiable data registry. So we'll switch to Trustchain being that verifiable data registry. And the first step is indeed just receiving the key. And they can check that that's a valid signature on the credential with that. But the question is it a valid key for that issuer? Is it really the university? So in addition to receiving the key when they resolve this from the data registry, there is also a signature with the key in the document metadata, and a controller who made this signature. And as Tim mentioned in the outline of this, in this particular case, it would be DFE. So what the software can now do is it resolves the DID that purports to perform the signature on the key of the issuer, and they can check that that is indeed a valid signature on the issuer's key with a key that was in the upstream entity that's just been resolved, DFE in this case. This now moves up the chain, this trust that's being placed into DFE here, and we now look for a signature associated with the resolved key from DFE and the controller indeed of that key, and we resolve that DID to go up to the central authority. And when we resolve the central authority's DID, we get back a key which allows us to verify the signature associated with the DFE key, but this time there's no controller because the central authority is in fact a root of trust. So the verification here involves checking that the timestamp associated with the embedded, where the DID is anchored in the blockchain is valid, and it matches the timestamp that is widely known and pre-configured. So if all of these things match, then the employer can be satisfied that both the signature is valid and the key, they can get the key and it's a key that has trust associated with it. So we can now see, just before moving on to the security and robustness, we can see this in action in the Trustchain command line app. So if we just remind ourselves what the VC looks like, it is this one for Jane Bloggs at the University of Oxbridge, and it has this proof. So this, and the starting point for the lookup is the issuer here. So the Trustchain app makes this very simple to work with though, and we already saw earlier that the VC verify command can be used by just passing in the credential file. But earlier we just also used the signature only flag. So this time we will not use that flag and allow for the full verification process. So if we do that now, the output is 2 lines. I'll just scrub that so we can see more carefully. So we get 2 lines. So not just the proof being valid from the key, but also now that the issuer itself is valid in this case. So that reiterates that final assurance. To look at this in more detail, if the verifier wanted to do so, to understand the chain of trust associated, a verbose flag can be passed in too. And this time, as well as getting that the signature is valid and the issuer is valid, that non-verbose output, the chain of trust is also is printed out. So we can see that the leaf node, the issuer here, is level 2, what their DID was, and then the associated signature on their key was done by DFE, and that was valid. And then lastly, the gov.uk for DFEs was valid. And at the top here, you get the timestamp printed out, which is key because that should be something familiar to the verifier. In fact, this can even be looked up, the transaction associated with that embeds this root, this gov.uk root. So we'll go to the block explorer. So this is all on testnet because this is all just testing and not real, of course. And we can actually see this transaction embedded. So the first thing of note is that it's got the same time here as the one that was reported. And then if we go to the op return associated with this transaction, we actually see that it's ION, and there are 9 other ION DIDs operations embedded in this, but these can all be looked up at this IPFS address. And then lastly, something of note is this was done over a month ago. So there's been nearly 32,000 blocks since this one was embedded. So a back of the envelope calculation shows that this would be, if this was on mainnet, would be about $3.2 billion to overcome. So it's very immutable. Okay, so We can return to the slides, and now we can just look at some security and robustness demo of this. So a sort of trivial case that's captured with Trustchain is, of course, if the signature itself is not valid. So if it was not a valid signature for the key associated with the issuer. So this would be returned in that first line, and we'd get across there saying that this was an invalid proof. A second, more Trustchain, something that Trustchain basically allows you to show that it's not valid is if the signature is valid, but the key isn't actually corresponding to the endpoint that it purports to be. So if we imagine a scenario here where there's a fake Oxbridge and someone's just set up a DID that's claiming to be Oxbridge, what would happen? So we can look at this very with the app. If we do the attestation again, and this time we'll pass in a bad DID. So I'll just copy that. Great. So we can look at this, and of course this looks valid at glance because it's got, it's been constructed with the same process, and it's the DID that in itself is not valid. If we now try to verify this using using Trustchain, so we pass in our credential. I'll just clear that so we can see more clearly. So the signature checks out, but the issuer this time has been flagged as not valid, and this is because it doesn't link back to a valid root. This robustness also extends to more complex attestations where there could be a chain of these fake DIDs, and unless it matches the correct root time or the correct set of root DIDs, it will be flagged as invalid. Okay, so lastly, we'll just move on to future plans for Trustchain. So we've demonstrated a command line app. We'd actually like to extend this to a mobile app, and this will be this mobile app will be for receiving and presenting and verifying credentials. You can see a sort of a prototype here provided by the Credible app from Spruce ID that we hope to build on. And the Trustchain version of this will also include so timestamp verification on the mobile, so that the DIDs themselves can be verified. And this will be made possible on mobile through a light node being available, which is much less, requires much less storage. As can be seen in the app demonstration here, where a QR code is being scanned for a VC endpoint, there's this question: do you trust this host? And Trustchain will have a natural answer to that because the DID that's scanned can be checked for its chain of trust. So with that, I'll stop and we'll take any questions.
Yeah, thanks, Sam. Just a note: I've put in the URL of the GitHub link. So this is now a public repository. So and there's quite a bit of more information on there. There's a wiki for anyone who's interested.